Hi, this is our last video from section 2.5, and in it we're going to take a look at Hooke's law, which can be used to calculate the work needed to compress or elongate or stretch a spring. And so if you look at the picture here in figure 2.51, the top picture shows a spring that's in equilibrium. Basically, it hasn't been stretched or compressed. And when that's the case, we think of x as 0. When the spring is compressed, we have x is less than 0, and when we stretch or elongate the spring, x is greater than 0. And what Hooke's law says, it's right below here, it says the force f of x required to stretch a spring x units beyond its natural length is f of x equals k times x, where k is a spring constant. So k is going to be some different value depending on how stiff or relaxed the spring is. It does say that the value of k is always positive, and it depends on the physical characteristics of the spring. And so we have example 6 here we're going to take a look at. It says a spring has a natural length of 20 centimeters. Suppose that a 25 Newton force keeps it stretched to 30 centimeters. And one thing we want to remember is what we know about units. So remember, work equals force times distance. Remember, the units on force is newtons, and typically the units on distance is meters. And a newton meter, do you remember what that is? A newton times a meter is a joule. And notice in this problem, it gives us our lengths in centimeters. So we are going to need to convert those both to meters. And remember, there is 100 centimeters in 1 meter, which means in order to convert these to centimeters, you're going to have to divide by 100 or move the decimal place 2 places to the left. So 20 centimeters is equal to 0.2 meters. And likewise, 30 centimeters is 0.3 centimeters. Okay, so let's use Hooke's law. Hooke's law says that we have this function for the force. It's f of x equals k times x. And we have the information that we need there to find what the spring constant is, because we know that it says a 25 Newton force. So that means f of x is 25. So 25 newtons is equal to k times x. And remember, x is the units that the spring is stretched beyond its natural length. And it says that it is stretched to 30 centimeters, but its natural length was 20 centimeters. So if you take 30 minus 20, 30 minus 20 is 10 centimeters, or 0.1 meters. So our x is going to have to be 0.1 meters, or 10 centimeters. And then you just solve for k. You divide by 0.1, and you get that k is equal to 250. 250, and that's newtons over meters, which means our function is equal to 250 times x. And then we can calculate the work. So remember, work is equal to the integral of f of x dx. And in this case, our function is 250x. And we're trying to stretch the spring from its natural length of 20 centimeters to a length of 25 centimeters. So x is going to go from its natural length, which is, remember, x is the units beyond the natural length. So if it's at its natural length, it is 0 units beyond its natural length, and we're stretching it to 5 centimeters past that. So it's going to be 0.05 meters. 0.05 meters. And so then we go ahead and integrate, and we get 125 x squared from 0 to 0.05, and that comes out to 0.3125. So pretty simple, straightforward. If you want to do the second part, it's basically the same idea, but our limits are different, right? So if we're stretching from 25 to 30 centimeters, then that's going to be, our limits are going to go from 0.05 to 0.10. And we still have same function, 250x, and I'll let you do the details on that, finish that problem. But this answer comes out to 0.9375 joules. And that's how you do Hooke's law. So that should be enough to get you into the homework or the lab assignment. As always, let me know if you have any questions on this section, section 2.5, and I'll see you next time. Thank you.